So yeah, first of all, thanks to the organizers for having me here. And thank you all for staying on Friday evening, 5 o'clock. There's a raffle afterwards,
Yes.
so that's some motivation.
You get to enter 3 times.
Okay, so in today's talk here, I'm going to talk about some of the impact, right, from HPC perspective that we are making at Schlumberger in terms of fueling fast and cost-efficient simulations as well as visualization. And so a little bit about myself. I am a HPC and 3D visualization manager. I focus on innovation. So Schlumberger by itself is an oil field services company. We provide technology for oil and gas exploration, drilling, production, and pretty much essentially the entire space, right? And so the center here that we have is an innovation center. It's at the Sand Hill Road in Menlo Park. And the focus is to bring the latest computer science technologies, partner with universities as well as some of the Silicon Valley company and apply those technology and innovation to the oil field domain. My background is computer science. I have a PhD from University of Illinois, Urbana-Champaign. My advisor was Professor Sanjay Kale. Some of you may know him. Charm++, if that sounds familiar, some of you. I also teach cloud computing at Santa Clara University and also consult in my part-time. So a couple of these numbers here, does they raise any thoughts in anybody's mind, what these numbers are? So related to computing, we're talking HPC here. Right. Okay, so this is petaflops. Yeah, so this is basically the R peak, 200.8. Okay, my pointer is here. So the 200.8 is the R peak of Summit, the number one supercomputer, and then 143.5 is the sustained with the LINPACK benchmark, right? So just throwing out this number, kind of generating some interest. But so 18.5 petaflops double precision is kind of some of our work with HPC in cloud. So that's kind of comparing that to some of the number one supercomputer kind of falls around like between top 15, I would say, supercomputing. So in a nutshell, if you are not able to stay for the entire time of the talk, I just want to tell you what I'm going to talk. Essentially, 3 important things. The first thing I want to kind of talk is in terms of the elastic and scalable, cost-efficient, high-performance computing in the cloud. Now, when I'm saying HPC, some of you may just think about your tightly coupled MPI, communication-intensive applications. Here, some of our applications may not be that tightly coupled. It may consist of jobs, which maybe some of them may be small scale, but we have hundreds or thousands of such jobs, which all need to run, right? So one of the example of that work is the seismic processing in the cloud. So seismic processing, for those of you who may not be familiar, essentially think of it like sort of a CAT scan of Earth's subsurface, and the goal is basically to generate the Earth's subsurface structure to figure out where there is a possibility of a reservoir, essentially with the goal of figuring out where the oil reservoirs are, right? And so the way it is done is by doing, first of all, you do seismic surveys, which send out some of the seismic or sound waves to Earth subsurface, and then you measure the sort of reflection, so you get sort of raw data, and then run the computation, denoising, all types of algorithms. And that's what essentially is seismic processing in a nutshell, right? So the second aspect of my talk is about high-performance remote visualization. So some of the work that we have done in the visualization space, so moving from traditional desktop visualization, which is common in the oil industry, to more of a cloud-native scalable visualization, where the rendering happens on the cloud, and then you are just streaming sort of the images to the browser. The third aspect, if we have enough time, that I want to talk about is more towards how we are using containers and Kubernetes and the kind of that infrastructure to achieve some of the high throughput simulations. So use cases where we have essentially small simulations, but then we want to run multiple realizations of those simulations for high accuracy and exploring things like uncertainty and optimization use cases. So I'll talk about specifically optimization of oil field production networks, where we have not like computer networks, but essentially networks of pipelines and equipments which are used for transferring oil from the place where it's produced to the place where essentially it can be refined or it can be used, right? So the bottom line is that HPC is enabling oil and gas companies to explore much needed energy resources and essentially to deliver those to consumers with faster speed and lower cost. And one of the things that is enabling us in the cost side is to use some of the cloud processing power and use the pay-as-you-go kind of model. Okay, so kind of first talking about the seismic processing and the cloud work that we have done. Schlumberger is, as I said, an oil and gas technology company. We have been there for years. We build technology for oil exploration, drilling, production, and many other services. So to some of the computer scientists in this room, this may be interesting, right, in terms of the data volumes that we have. Out of all these services, the oil exploration, which is the seismic data, is the most larger scale, essentially. So as you can see, the seismic data, whether it's onshore or offshore, so basically it can range to petabytes of data per project, and then you can have multiple projects per year. That's the kind of scale that we have in terms of the data. Now, there are other domains such as well data, where essentially when you're drilling the well, and basically as you're drilling, you kind of want to take the measurements about certain properties such as porosity or the properties of the rocks as you're drilling downhole, or also like the things like pressures and temperatures for certain simulations. Then you also have the production data in terms of data about the pumps, pipelines, and so for instance, these are small per well, but then you have large number of wells, which can make it large. So seismic exploration, in a nutshell, as I said, basically the first step is the data acquisition, and then you kind of build the subsurface understanding from the data. And so essentially, as I said, the large amount of data that is recorded could be 20 to 100 terabytes in one job, for instance. And then this processing consists of large number of compute and I/O intensive jobs, which can run concurrently. We have, like for instance, one small job can use hundreds of nodes for several days, and then we can also have large jobs such as those requiring 3 to 5 million core hours. So which can have thousands of nodes for that kind of processing. So Schlumberger has software which does seismic processing, and so that particular software is the traditional software basically is Omega. And one of the things that we did at the Innovation Center here was to kind of collaborate with some of our partners, NVIDIA and Google in this case, and essentially transform that processing from the in-house to the cloud, right? And why do we want to run in the cloud? Essentially, it enables us sort of the elasticity and scalability. We don't have to maintain the data centers and keep them running at the peak demand. But what we can do is we can scale up and down as and when we have jobs which need large amount of infrastructure. Now, the key requirement for us is that when we have a job, we want to make sure that we can provision that infrastructure dynamically in a very short amount of time, right? So that's where essentially we use Google Cloud in this case, and then GPU nodes along with the regular CPU nodes. So the time to decision is a competitive advantage, and we can also explore like increased number of scenarios by running all those things in parallel. So quick view on Schlumberger seismic software stack. We have, as I said, we have traditionally data centers, clusters of CPUs and GPUs. So our software runs algorithms which are not just one particular algorithm, it's a mixed suite of algorithms. And we have essentially file systems, layers of networking. The software stack is fault tolerant. And we have custom job schedulers for this case. Now on the Google Cloud platform, the way that we basically run is that we have, if you see in this picture here, we have these sort of three tiers here. So the bottommost is the distributed file system. So we have certain nodes which run cluster. Then we have at the top, we have a set of virtual machines which are durable infrastructure that we have all the time. For instance, some of those are needed for logging purposes and so on. The cluster manager nodes here. And then the majority of the infrastructure is ephemeral dynamic, which is created on demand based on when we need. And that infrastructure consists of a mix of different types of VMs. We do use GPUs extensively because we get a great performance per dollar for seismic processing some of the algorithms here. And the computation, as I said, these instances are dynamically created. Of course, it's a large system, so we do want monitoring and control. We use some of the Google internal tools in some cases, such as TechDriver. Now, one of the challenges that you'll see when we're talking in terms of terabytes and petabytes of data is to, of course, you can do that processing in the cloud with so much better performance or maybe reasonable performance, but then you also need to make sure that the data that you have, when you transfer that data to the cloud, that could be bottleneck in many cases. So for that reason, we needed to have a high-speed link between our data centers to the cloud. And of course, security is an important component during the whole process. To give you kind of a glimpse of some of the workload running, so this chart here, so x-axis is kind of the time. It's a few days, right? So 7 to 14 days. And then the resource count is the number of nodes or servers which are running at any particular time, which are in use. So the green here is busy, so the nodes which are busy. The yellow is kind of idle. Some of the nodes that we keep idle for specifically, say, for debugging or troubleshooting in any particular case. Red is some of the nodes which failed. So as you can see here, for instance, we can scale from close to zero to close to 5,000 or 4,500 nodes, and this is within a matter of 1 hour here. So we use this kind of bunch of different types of nodes, and it's not just one type of node, as I mentioned. It's a mix of CPUs and GPUs. We do use up to 7,000 GPUs in this case. Yeah, and then of course the I/O is another critical component here, so up to 220 gigabytes per second in this case. So this is one of the three components that I wanted to talk about: seismic processing in the cloud, very computationally intensive workload. Yeah, question.
So the workload is embarrassing in parallel. They're not communicating.
Yeah, to the most part, right? Yeah, in this case. Yeah, so this is, as I said, it's a mix of different types of jobs, and most of the jobs are essentially embarrassingly parallel. So there's no not communication. Some of them, a subset of those could be communication intensive, and for those, we have to kind of maintain the scale.
On the previous slide, due to fault tolerance,
Mm-hmm.
or do you restart these things midway? You have checkpoint quota? What do you mean by that?
Yeah, so essentially, basically, to my knowledge, and Dave is here in the room, he may know better than me because he has worked on that a lot. But my belief is that we do some sort of checkpoint restart. Is that true, or no checkpoint? Okay, but restart.
It is a custom version, custom version that produced with some logic that will redo the work all over, but enough collection along the way that we don't have to redo too much. So it's very hand-tuned for the particular application structure rather than generic approach.
Okay. Any other questions at this point? Okay. Let's move on. So the next aspect that I want to talk about is when we build this model of the Earth, right? The next step for us is really to visualize that. Because once we can visualize that in 3D, then the geophysicists or the seismic interpreters can look at these models, and then that's where they can interpret them and identify where there are interesting aspects, and based on how the Earth's structure look like, they can make certain predictions. So traditionally, some of our visualization software has been basically we have durable infrastructure, we have local data shared file system, and essentially we have mostly sort of desktop visualization software that you can install, and then there is that challenge there that essentially from the time that you generate the data, right? So you have the seismic data that is generated to the time essentially you can visualize. So basically you have these tapes and disks that you have to sort of move, and that data movement is an unproductive activity which can take days or even weeks in many cases. So that's the kind of model that we want to get rid of and essentially get to the next generation, which is essentially having a sort of visualization API where we have these dynamic virtual machines which are generated on the fly. They do have use GPUs in the cloud, and the data is stored in the cloud storage. So your seismic or other kind of data, not just seismic, but you can have other kind of oil field objects such as wells and other surfaces and so on. So those data could be stored in the cloud storage, and then dynamically as a request comes, you can spawn a virtual machine which reads the data. And I'll kind of show you a video of a demo of that. But the idea is to have this everything happen spontaneously so that you don't have to wait for that data movement to happen. And the user could sit anywhere, could have a thin client, could be a mobile device, could be an iPad, could be a laptop, but the user doesn't need to have a powerful server in this case, as opposed to the traditional approach where you are doing sort of client-side visualization, where the data, all the data is coming to user's machine. And think of it like the analogy I kind of like to give is sort of before Netflix was there, for instance, you would have these, if you want to watch a movie, you would go to a store, get a DVD or VHS, and then put it in your system and basically start watching. If you don't like, then you have to do that round trip again. Similarly, and then of course after Netflix comes, now you have like a library of movies which you can select, and instantaneously it will load. The similar kind of model is something that we are applying to the oil field visualization, where instead of having that data and tapes to ship, you can have like a catalog of oil field data that our customers can see, and then if they as they have subscription, then once they click, they can just see that. So for instance, here there is a video which is kind of showing here. Basically, it's in a browser, and then the red sort of rectangles and triangles are reflecting some of the oil field data. So in this case, they are seismic surveys which are done at that particular location. So if I just click on that, it's basically creating, what it does is it connects to the cloud, So the service is running in the cloud that we have, and it launches a virtual machine if it doesn't exist. In some cases, we proactively have some VMs running to minimize the time. And then basically the data loads instantaneously. Now, of course, in some cases, the data is large. So it can have, say, hundreds of gigabytes of data. And of course, you can't fit everything in memory. So we do some sort of level of detailed kind of thing where as you are far, you will see only the lowest resolution. As you sort of zoom in, you can see higher resolution to basically minimize your wait time so that we don't load the entire data into the memory. Yep.
Question about your data set. You have density, right? That's basically the only thing that seismic data gives you is the density of the three-dimensional point. Acoustic impedance, which is
right.
something constant. So you don't know anything about shear stresses, or maybe you can infer that from the local structure.
You're mostly getting the shapes of the formations, not directly the properties. Everything else is either fully constrained or indirectly.
I guess what I'm getting at is, do you have information about the four-dimensional future of the structures? I mean, can you look at something and say, oh, that's going to collapse?
Other parts of the company will build geomechanical models which will attempt to predict that sort of stuff.
Yep. Yep.
Did you guys end up using like index or is this volume rendering or right? So did you guys use it?
Yeah, so actually I have a next slide on index as well. Are you referring to the NVIDIA index technology?
Did you use GVDB as well, the OpenVDB like stuff that NVIDIA has for?
Not that, but we did explore with index. So this is, as I said, this particular one is doing sort of level of detail-based visualization, so it's not showing the full resolution. And then we also tried out the NVIDIA index to see.
We also have a volumetric database, like not really a database, but it's a volumetric format. It's based off of OpenVDB from
Right.
reports. Did you guys end up using that for your report?
Yeah, I have the next slide on some of the NVIDIA index work. Yeah.
What kind of user products are integrated with Delphi? Which red, intersect, fixed, omega? What kind of?
Yeah, so again, I'm not a salesperson. I'm an engineering person here. But then, of course, we have this Delphi umbrella, which is our next generation product offerings. And some of them, the public ones are definitely out there, as you said. So Intersect is there, which can run in the cloud. Then, of course, we have Petrel in the cloud, which is essentially, what it does is basically you can have the Petrel software, and it is running as a VM in the cloud, and you connect to that. But then this kind of becomes a cloud native visualization offering as it comes along, right?
What's about intersect?
Right, so Intersect and Eclipse, as you said, these are reservoir simulation software for everybody's reference. So, and that is one type of application which is more communication intensive, right? So that is not embarrassingly parallel. It requires like a high performant network, right? So in that case, I think the public one we already have out is with Microsoft Azure. So you can run Intersect in Azure today. Any other questions? Okay. Okay, so I'll move. How are we doing on the time? Okay, so I think it's doing fine. Yeah. Okay, so the next thing, as I was referring to, was we also tried full resolution visualization using index, where you have, so this is your browser, and then you have essentially multiple VMs which are doing distributed rendering. So the previous demo I showed was basically there was only one VM with one GPU, which is doing the visualization, but we can extend that to have multiple instances of virtual machines and multiple GPUs using NVIDIA's index distributed rendering. And basically, the data set is kept in memory across the entire cluster. The larger the cluster that you have, you can load larger and larger data. It's proven to scale to petabytes of data. Of course, there is the cost of GPUs, because as you are running more and more VMs with more and more GPUs, it can be pretty expensive. So there is this trade-off between the visualization that you want to have versus the cost that you are willing to pay. Right? So this is one in particular case, one of the data set that we visualized using index with 16 GPUs, I believe.
What's the resolution on this?
Sorry?
The frame resolution?
Let's see. Do you see anything here? Okay. Okay, so I'm not sure it's here. I can check and get back to you about that. Okay. So the next thing I want to talk about, which is the third thing that I mentioned in my start of the talk, is about how we are using containers and Kubernetes, applying those for some of our simulation software. So to set some of the stage, essentially, Schlumberger is, as I said, in the business of this exploration, right, which you kind of saw in the seismic acquisition, and not acquisition now, but seismic processing. But then also in terms of building this or helping build the infrastructure for bringing the oil down from downhole and all the way to essentially where it can be used, right? So in terms of having these simulation software which can help you predict and optimize the production of oil. And it is a massive feat of engineering to build such sort of an infrastructure to extract and transport the amount of fluid to the processing facilities where it is converted to consumable products. And these infrastructure are a complex network of thousands of miles of pipelines and production equipment that can span continents and seas and require sophisticated controls. So one of the things or the software that we have is called PipeSim, which is a multi-phase flow simulation software. So you have fluid, which is a mixture of you can have gas and oil and water. So it's multi-phase, and then basically we want to simulate with using software tools to simulate the flow of oil, gas, and water under varying conditions and control settings. So if you see, you have, say, hundreds of wells, and then you have pipelines connecting them, and each well has certain parameters that can be controlled, such as the pressure and sort of choke points and things like that. And then that kind of entire thing becomes a system. It's a network from a production perspective. And based on how you tune these parameters, you can change the total overall production, oil production for your system, right? So then this software essentially applies high-performance computing techniques to solve these equations of conservation of momentum, energy, and basically helps us do that. As I said, the use case is the optimization that I'm going to talk about for production networks. So while you have this system of, say, wells, so you have 100 wells, each of them is basically kind of has certain parameters that you can tune. And for each configuration, you can use the simulation software to sort of estimate what will be your total production. But then because you have these 100 wells, and each well may have, let's say, even, say, for instance, if it has 5 tunable parameters, then you have these 500 variables, and your system is the combinations and permutations, if you see, would be very large. And if you want to come up with an optimal solution, so you want to optimize for your total overall production, the number of possibilities that you have to try out kind of grows exponentially. And for each of that possibility, you have to run a simulation to get or estimate what will be the total production. So the kind of problem that we have becomes very large. So for instance, here it's kind of showing you this system, right? So you have these wells here at the left, you have in the middle, and then here. And then each of these points, for instance, these are kind of the choke points. And then basically they're connected here to the facility. So you have this entire sort of network. And one of the things that we have done from the innovation perspective is, rather than solve this entire system as a whole, we can break down this into sub-networks. So for instance, this is a sub-network, this is a sub-network, and these three are sub-networks. And you can solve each of these sub-network problems independently. And then you can do some set of iterations to make sure that basically you get, when you solve each of them independently, you get certain parameters which are optimal for this subnetwork. And then you have to bring those all together to make sure that you have a consistent convergible system, right? So that can take a few iterations. Now the good thing about this part is that when you break it down into subnetworks, these can be solved in parallel. So you don't have to do all of them sequentially, so you can do them in parallel. And that's where we can use some of the scaling or elasticity of cloud with containers and Kubernetes to solve these in parallel. So the system that we developed here, essentially, so we have this sort of a front end with a Cupid AMQP broker, which receives requests. There's a front-end web service using Flask and Nginx. And then you have this optimizer service, which will listen to the optimization request. And then you have a subnetwork optimizer service. So subnetwork will work only on the small subnetworks. And then it will run the network simulation. And then you can have a bunch of these running in parallel. And each of these network simulation, which is the pipe simulation software that we have, that internally also uses MPI for scaling. So we have this, each of this is MPI simulation, and then you can have multiple of those. They can all run in parallel, and then you can have these multiple of subnetwork optimization running in parallel. And this is all running, these are basically individual Docker containers running in a Kubernetes cluster. So in terms of some of the results in this particular case with the optimization solution, so the blue curve here, first of all, the y-axis is the time to optimize for the total solution. The x-axis is the network size, which is the number of wells. So as you are growing from, say, here to here, you are kind of making the problem bigger and more complex. So the blue curve, as you see, kind of grows exponentially here as you increase the number of wells. Right? So the time to optimize kind of grows to very large, and we cannot solve it in some cases. If we have large number of wells, it can take days to solve the problem. The red curve is where we do it using the decomposition algorithm. So we break it down into subnetworks and solve those subnetworks independently. But we're still using, basically still running everything on a single machine. So we are not really using full parallelization potential. And the yellow curve is where we run it in the cloud or in an infrastructure where we kind of scale based on the application need. So as you get more and more work, so basically as you launch more containers, automatically it can auto scale, and it can launch new VMs which can run as basically run this workload. So the yellow curve is where we kind of get this scaling for the subnetwork decomposition, which runs in parallel. So yeah, so I think sort of coming to the conclusion, and I think I'm good on time here, in a nutshell, I talked about three aspects where we are applying HPC and visualization to some of the innovation that is happening within the oil field industry. The elasticity and scalability of the cloud, remote moving from client side, limited size visualization to a visualization of large data set with remote and using GPUs in the cloud. And then the third kind of model where we have to run these multiple simulations for a variety of reasons, for exploring multiple realization in some cases. In some cases, it's basically trying out with under uncertainty, but we can do that by starting small and let the infrastructure kind of scale based on the demand. And the last slide, I think, sort of want to thank you all for listening and a call to engage with us. As I said, we are very close here on Sandhill Road in Menlo Park, and definitely as a mission that we have, we are definitely interested in assessing and adopting the latest HPC technologies. So I was very happy with all the talks, and we kind of learned a lot about container technologies, AI, everything in the last 2 days. And some of those we would definitely want to collaborate and have some partnership around that innovation. We would be happy to host and meet you at the STIC Center that we have here. Feel free to reach out to me or talk to me. I have Dave and Rod here from Shamaji here as well. I'm also the organizer of HPC in Cloud meetup, Bay Area meetup. So actually, I think Ebru here, we have kind of exchanging messages, kind of organizing a meetup. So definitely, if you want to present there, some of the talks will be definitely interesting there. And just a last point about recruiting, I'm also recruiting for HPC and visualization engineers here. So thank you again for listening and being here on a Friday evening. And we can have some more questions here. Yeah.
What precision arithmetic do you need to do the reverse time
migration? Yeah, so the reverse time migration, I think traditionally, I think we are using single precision.
We're traditionally using single. People at Stanford have done some experiments using half 16, so 16, and if you're careful, you can do it. So 16.
Yeah, single precision. But we are looking into algorithms where we can do like, on a shorter.
And what size data is used for one job?
Mm-hmm.
Just one instance of that.
For seismic processing, I think it's terabytes of data.
For a single job?
Yeah, I mean for a single workload, which can consist of multiple of sub.
I mean,
Some,
one of those sub-workloads.
right. One of the sub.
Doing my head, 2 gigabytes per there's a few tens of thousands jobs and a few gigabytes each, maybe.
Right.
Adds up to a few terabytes.
Mm-hmm.
Add some better numbers.
Yeah.
So this picture is about 20,000 square kilometers. So the image that comes out is
Right.
20,000 kilometers square times 20 kilometers deep, about 10 meters long.
Yeah. Okay. Thank you again. And if there are no more questions.